All right. So let's get started. So today we'll talk about kernels, which is a very interesting technique to handle nonlinear decision boundaries, to handle it in a smart way from a computational point of view. And I'll start by discussing kernels in the context of geometric margin and perceptron. These are topics we covered last time. And then I'll also discuss kernel methods in the context of SVMs towards the end of the lecture. And as you probably guys know, SVM is another celebrated algorithm in machine learning with widespread applications and very solid foundations. OK, cool. So let me start by doing a quick recap of the Perceptron algorithm and the geometric margins. Okay, that's our core for the lecture today. And we've seen this last time. So the Perceptron algorithm is one of the simplest algorithms in machine learning. It has been known since the 50s. And it has originally been analyzed in the so-called online learning model. Okay, and I guess everyone here knows. So for most of the class, we've been talking about the so-called batch learning scenario, where we assume that all the examples are given to us up front, right? So for example, if you want to do spam detection or image classification, we assume that all the examples, say all the email messages or all the images are given to us up front, okay? This is in the typical batch learning scenario. Now, by contrast, in the online learning model, we assume that the examples arrive sequentially. Okay, so every day an example arrives, and we need to make a prediction. So for example, every day an email message arrives, and we have to predict immediately whether it's spam or not. And then at the end of the day, we are told the true label of that example. We are told it was spam or it wasn't spam. Okay, and this is the online learning model. The examples arrive sequentially. So we go for a number of rounds, potentially very large number of rounds. In each round I, the algorithm first gets to see an example xi, an unlabeled example xi, and then immediately it must make a prediction. It must predict the label of that example. And then after that, at the end of the day, we are told the true label for that example. Okay, so the true label is revealed, and then the online learning algorithm can use that information to then somehow update its internal state to learn something in order to do better for future examples. Okay, so that's the online learning model, yeah? And as we discussed last time, actually analysis-wise, traditionally, in this model, people make no distributional assumptions about the input sequence. So actually imagine that the input sequence is in fact an arbitrary sequence of example. It can even be adversarially chosen. Okay, and because we make no distributional assumptions about the sequence of examples, that means we cannot really talk about converging somehow, right? And instead, what we have to do from an analysis point of view, we need to we can do is to try to minimize the number of mistakes. Okay, we want to come up with an online algorithm that somehow minimizes the number of mistakes, and we can do so if the true labels are consistent with a target function that it's not wild, that belongs to a structured class of functions. Okay. So do you guys, actually we discussed this last time, but just to even further clarify, because there are a couple of questions at the end of the lecture. So do you guys see why we cannot talk about converging in the online learning model? Because say that you assume that you believe that you have a bound, that after t rounds somehow your algorithm converges, right? Then because the sequence is adversarially chosen, what the adversary could do can give us the same example for t rounds, just one single example, and give it to us, feed it to us for t rounds. We really don't learn any new information because we see the same example over and over again. And after those t rounds, the adversary can start giving us a completely different set of examples, right? So because it's online, because the sequence is adversarially chosen, we cannot really hope to talk about converging to a fixed function. But what we can do, and we show that we can do this in the context of perceptron for learning linear separators, right? What we can do is to minimize the number of mistakes. Okay, so I think this answered your question. You had the question last time about why can't we talk about converging. Okay, cool. So that's the online learning model. So, and we analyzed in detail last time the Perceptron algorithm for learning linear separators in the online learning model. So we also discussed in detail that we can always assume that the separator goes through the origin. As you're saying, we can always translate the origin, right? So this is of our loss of generality. And so this algorithm is really simple. It's a greedy algorithm. At each moment in time, we have a current guess for the target function. And we use that current guess to predict the label of a new example, right? So if a new example comes in, we just use the current guess to predict the label. If it's on the positive side of the separator, we predict positive, otherwise we predict negative, right? And then if we do make a mistake, we simply update as follows. If it was a mistake on a positive example, that means that basically our dot product here was negative, but it should be positive. So therefore, we update our current guess by adding that example, which then increases the likelihood that our current guess is more correct on that last example. Okay, so if it was a mistake on a positive example, we add the example to our current guess for the target. And instead, if it was a mistake on a negative example, we just subtract our current guess from the target. Okay, and we discussed in details reasons for doing so last time. Okay, cool. So that's the algorithm is really simple. You just keep a current weight vector for the current guess for the target. When a new example comes in, we use it to predict. If it happens, we only update if we make a mistake. So it's a conservative algorithm, and if we do make a mistake, we just simply update by adding the example to the current guess if it was a mistake on a positive example, and by subtracting the example from the current guess if it was a mistake on a negative example. Okay, so very simple algorithm. And I mentioned this last time, but this is crucial for the lecture today. An interesting fact about this algorithm is that at any given moment in time, our current guess, so the normal vector, WT, for our current guess for the target, it's a weighted sum of the examples on which we've made mistakes so far. Okay, so basically you can easily show that the current, so at any moment in time t, so after t mistakes, after a number of mistakes, I should have had here t actually. After t mistakes, the normal weight vector is basically the weighted combination of the incorrectly classified examples, right? Because we start with all zero vector, and we only update our weight vector if we make a mistake. We add the example if it was a mistake on a positive, and we subtract otherwise the example if it was a mistake on a negative example, right? So for example, let's assume that the examples on which you made mistakes, xi1, xi2, xik, they're all distinct, just different vectors. Then, for example, if the very first mistake was a mistake on a positive example, then this coefficient here would be what? What would be this coefficient? +1, exactly, right? So if this was a mistake on xi1 was a mistake on a positive example, this coefficient would be +1, right? Say for the last one, say that this was a mistake on a negative example, then the coefficient will be -1, right? So it's easy to verify that at any given moment in time, the current, so the normal vector for our current guess for the target, so WT, is a weighted sum of the incorrectly classified examples. Okay, now why is this interesting? Because, well, it turns out that in order to predict the label of this example, of a new example, right? If when a new example comes in, we need to be able to use that current guess for the target to come up with a prediction for the label. Well, in order to do so, what we have to do is to be able to compute dot products between the new example and the examples on which we made mistakes, right? Because if I write down a WT.x, it's basically this weighted sum of these dot products between the new example and the mistakes, just from the linearity, right, of the dot product. Okay, cool. So that's now number one, and will become important in a bit, in 5 minutes, when I talk about kernels. And also now number two, and this is actually also very important for kernels, is that we proved in detail last time that the number of mistakes that the perceptron algorithm ever makes depend on a sequence of examples, depends entirely on the geometric margin of that sequence of examples. Okay, and so basically the number of mistakes that the perceptron is ever going to make, it depends just on the margin, the geometric margin of that sequence of examples, and it's independent on how long the sequence is. The sequence could be a very, very large in size, and it's also independent of the dimension of the ambient space of our examples. I mean, our examples can really live in a high-dimensional space, in three-dimensional feature space, and really the number of mistakes that perceptron will ever make just depends on the geometric margin of that sequence of examples. Okay, and just a very, very quick recap. I'm going to go quickly through this because I went in detail last time, but just because it's crucial for today, I want to quickly recap what the geometric margin is. Okay. All right, so what's the geometric margin? Well, it's the most natural notion of margin you could think about. So if our examples lie in a Euclidean space, then, so given a separator, like this one here, specified by normal vector W, the margin of an example X with respect to my linear separator specified by W is simple just the distance from my example X to the separator. Yeah, so it's margin, right? By how far you are from the decision boundary, essentially. Okay? And it's a fact about geometry, and I used it last time. It's just an elementary fact about geometry that if we normalize the normal vector, so first of all, I'm only thinking about homogeneous linear separators right now. I said it's a value of generality, right? And because of this, I can just always renormalize the normal vector to have length 1, obviously. But if I do this, when it turns out that the margin of any given example X is just the absolute value of the dot product between my example X and the normal vector W. Okay, and this is just a basic fact about geometry. Okay? Good, so that's the margin of an example X. It's just the distance from the example X to the separator. So the margin of an example X with respect to a separator specified by normal vector W is just the distance from the example X to the separator. Okay, and now given this is the margin of an example X with respect to a linear separator, now what is the margin of a set of example S with respect to a linear separator? What is that? So now if I have a set of examples, and I want to talk about the margin of my set of examples with respect to a linear separator, what is the margin? Somebody volunteers? Yeah, it's written on the slides, but maybe somebody, yeah?
It's written like that. This is the margin.
It's the minimum margin. So I'm thinking, right now I'm still fixing a separator W, a separator given by normal vector W, and I'm trying to think about what's the margin of a given set of examples with respect to that separator. Well, that's the minimum margin of an example X in my sample with respect to that separator, right? That's the margin with respect to a set S of a linear separator, and then what's the margin? So now if I just drop the linear separator W and I'm just asking what's the margin of a set S, then, as you said, is the maximum margin over all possible separators with respect to the set S. Okay, so is the notion of margin clear? Yeah, I think so. Good, so there's the margin. And we proved in detail last time. Okay, what's going on? Okay, here it is, good. Right, and so we showed last time in detail, it's luckily, so for this perceptron algorithm, there is a very cute, simple, intuitive geometric proof, right? And we proved in detail last time that if the data is linearly separable by margin gamma, then the number of mistakes that the perceptron algorithm will ever gonna make depends entirely on the margin. So in particular, the number of mistakes that the perceptron algorithm is gonna make is at most R squared over gamma squared, where gamma is the geometric margin of a set of examples, and R is the maximum norm or the maximum length of an example. Okay? And we showed this in detail last time. And it's actually a very, very nice geometric intuitive proof of why margin is important. And also just as a comment also, I mean, another way to think about the margin is just kind of the amount of wiggle room available for a solution. Okay, just rephrasing what that means in more intuitive terms. Okay, great. So that's a guarantee. So if we do have a large margin, so right, so if gamma is large here, right, then it means it's like gamma is not too small. That means the perceptron algorithm is going to make not too many mistakes, right? This is an implication, right? If the margin gamma, for example, is a constant, then the perceptron algorithm is only going to make R square mistakes, or R is a length of the maximum length of an example, okay? And so again, the interesting fact here is that the number of mistakes does not depend on the dimension of the ambient space. Depends only on the margin, depends only on the amount of wiggle room. And this is true no matter how long the sequence is. Okay, so this is a kind of a guarantee that shows that if we do have a large margin, then the perceptron algorithm is going to behave well. Okay, and actually Tom made a comment last time, so right, so the argument that I wrote here on the slide, the statement that I wrote on the slide here, it's holds for the case when the data is linearly separable, and moreover, the way the statement is written and what we showed is actually for the online learning model. So this is a mistake-bound guarantee, right? Now, and just a couple of comments. So, oops, what did I do? I want to go back one slide. Okay, just a couple of comments. So it turns out that we can also, so right, as I mentioned, the statement that I put down on the previous slide holds for the online learning model. Okay? Now, what if I have a fixed data set of examples, S? Turns out that I can still use the Perceptron algorithm to find a separator that is consistent with my set of examples, if a separator exists, right? Say that I have a set of examples S, and let's assume that my set of examples S has a large margin, gamma. When I claim that we can use a Perceptron algorithm, in particular, we can cycle R squared over gamma squared plus 1 times through the data set, and then we can output, we're going to be able to output a separator that is consistent with my set of examples. Okay, so we can use the Perceptron algorithm to also solve the so-called consistency problem. Okay, so that's one comment. I'm just going to go through these comments. I'm not going to prove them. I'm just going to mention them. They have proofs. I'm going to post online some lecture notes. If you're curious, there are proofs in there. Okay, cool. So we can also use the Perceptron algorithm to find a consistent separator of a given data set that is linearly separable by a certain margin. Also, we can also, if we actually can also use the Perceptron algorithm to get a distributional guarantee. So if our examples not only come online, but that come from a fixed but unknown distribution, then I can also talk about how many samples do I need to see. I only need to see like 1 over epsilon times R squared over gamma squared samples coming from my underlying distribution to then guarantee that after the classifier that I get after so many examples will have small error rate on new samples that come from the same distribution. Okay, so typically if we have an online learning guarantee, if we can guarantee that the number of mistakes is not too large in an online scenario, because online learning is more difficult, we can immediately translate it into kind of a distributional learning guarantee. Okay, and we can also do the same for Perceptron. And moreover, and I'm not going to go through this again in detail, but just want to mention, it turns out that we can also adapt the mistake bound argument for Perceptron to also hold for the case when the data is not perfectly linearly separable, but almost linearly separable. Like in other words, the total distance we have to move the points to put them on the right side by the right margin is small, then I still have a small mistake bound for Perceptron. Okay, and the more interesting aspect for today's lecture is that actually the Perceptron algorithm can be adapted to handle nonlinear decision boundaries by kernelizing it. Okay, and you'll see this in detail. That's a very cool fact. Okay, so that's the Perceptron. So these are some nice facts about Perceptron. Before actually going on and talking about kernels, I want to spend a moment and talk a little bit more about large margins. Because actually kernels are only kind of meaningful once we have large margins anyway. Okay, so, and this will be a very intuitive discussion. I'm not going to go into details, but I just want to mention some very interesting implications of actually this theorem for this mistake-bound argument for Perceptron. Okay, cool. So I said this several times by now. So if the data is linearly separable by a margin gamma, then the Perceptron algorithm is only going to make R squared over gamma squared mistakes, no matter how long the sequence is, and no matter how high the dimension of the underlying feature space is. Okay, cool. Now, let's, so if we have a large margin, we have this online learning model, and if we use the Perceptron algorithm, things are great, right? That's the implication of this statement, okay? But now how about more classic distributional learning setting, right? Okay, how does this connect to things that we've seen, like VC dimension and uniform convergence bound and generalization guarantees, okay? And here is one way to think about it. Okay, so going back to linear separators, right? So we discussed this in the past. So the class of linear separators is not too complex, right? If I have linear separators in Rn, then we know that the VC dimension of linear separators is n plus 1, right? So VC dimension is a measure of complexity of our class of functions. If it's small, it's good, because we need a few examples to generalize well, right? And we proved in class that for the case on n is 2, the VC dimension is 3, okay? And I claimed that in general, the VC dimension of linear separators is n plus 1, right? And that was an extra credit problem in your homework. Okay, so what this implies is that actually there is a set of n plus 1 points that we can shatter. We can label in all possible ways of linear separators. But there is no set of size n plus 2 that we can label in all possible ways of linear separators. Right? So this is a sense in which linear separators are simple enough. Right? So in this context of shattering, right? Because as we've seen, the notion of shattering is crucial for reasoning about generalization abilities, for reasoning about classifiers that do well on the sample, doing well in the future as well. Okay, so right. So if we have linear separators in Rn, then we can shatter n plus 1 points, but we cannot shatter n plus 2 points. So there is no set of n plus 2 points that we can label in all possible ways. Okay, but how about if we require that the points are linearly separate? How about if we think about shattering a number of points with separators of a large margin? Okay, right? So how about how many points? So here's my question: how many points can you shatter, or how many points can you label in all possible ways by using linear separators that have a certain margin gamma? Right? Intuitively, if gamma is very large, like the margin is a constant, you'd think that this is potentially much smaller than the n plus 1, or an east dimension of the ambient space. Right? And it turns out that this is actually true. So if you think, and this will be a homework exercise for you, so if you think about it, what the Perceptron algorithm implies, the argument that I have for the Perceptron algorithm, the fact the mistake bound of the Perceptron algorithm is at most r squared over gamma squared, this then implies that we can have at most r squared over gamma squared points inside the ball of radius r that can be labeled in all possible ways, but separators that have a margin at least gamma. Okay, because if I had more than those points, so again, you think about this carefully offline, but just intuitively speaking, if I have more than these points, then I can always run the Perceptron algorithm, and because I can label the points in all possible ways, the adversary can always give me the label that is the opposite of what the Perceptron predicts on that example. And then I get a contradiction. Okay? So you'll go through this slowly in your homework, but I claim that the argument, the mistake bound for the Perceptron algorithm immediately implies that we can have at most r squared over gamma squared points inside the ball of radius r that can be labeled in all possible ways by separators of margin at this gamma. Okay, now this is not quite technically correct, but rephrasing what this statement here says is that basically kind of the VC dimension of the class of linear separators with a large margin, at least gamma, is at most r squared over gamma squared. So it could be potentially much, much smaller if gamma is a constant. Okay, and again, my claim about the VC dimension of large margin separator is not quite right. It's technically not correct, but it's the right intuition. Okay, so basically what this statement implies is that the large margin classifier, so if you think about large margin classifier, they have a much smaller complexity compared to the class of linear separators. So the linear separators of the large margin have a much, much smaller complexity. So the shattering coefficient is potentially much smaller, their intrinsic complexity is much smaller, and so that means that we have less classifiers to worry about that they look good on the sample, but really bad overall. Okay, so that means that basically the large margin classifiers are really less prone to overfitting. Okay, so that means that basically searching for, if we can, and if for our data sample set we can find a classifier of large margin, that's a good idea. Is this argument intuitively clear to everyone? Right, so I basically use the mistake bound argument for Perceptron to kind of argue that the shattering coefficient for large margin classifiers, so the number of ways of splitting, right, so the number of points that I can label in all possible ways with linear separators of a large margin is small, depends only on the margin, and it's independent of the dimension of the underlying space, which then somehow implies that these large margin classifiers have a much smaller complexity and they are less prone to overfitting, and so therefore it's a great idea to search for classifiers that have a large margin. So this is actually the right intuition. There are some details to handle, but it's really the right formal intuition to think about why large margin classifiers are good. Okay, cool. And so to summarize this discussion, basically, so this notion of margin, large margin, is a crucial notion, is a core notion in machine learning, very important notion in machine learning. We've seen that if, for example, in the online mistake bound model, if we have a large margin, then the Perceptron algorithm will do great. We're going to make only a small number of mistakes. And I also just made an argument intuitively, and people have formalized this. Actually, it was formalized even in the 70s by Vapnik. And so this was formalized even in the 70s, that if somehow, if we have a data set and it does have a large margin, and if our algorithm really finds a separator that has a large margin over the sample, then we are guaranteed that the number of samples we need in order to learn well, in order to output a classifier of small error, depends only on the margin and is independent of the dimension of the feature space. Okay? So just a comment, in its natural form, the Perceptron algorithm doesn't produce a separator of large margin. It behaves well if we have a large margin, but the separator that it produces, even when I try to use it to find a consistent separator, might not have a large margin. Okay? Necessary, but still has a small mistake bound and still good guarantees. Right? The second statement that I have over here says that if I do have a data set or an underlying distribution that does have a large margin, or nearly a large margin, if I explicitly look for classifiers that have a large margin because they have smaller complexity, then I'm guaranteed that the number of samples in order to learn well depends only on the margin. Okay, and this is actually, so this is a very, very core, it's a deep result, it's very interesting, and actually it was known since the 70s, and it was actually used in order to design the support vector machine algorithms. So the SVM algorithm that I'm going to talk about at the end of the lecture was directly motivated by this statement. Okay, by this deep understanding of what the margin can do for us when we have a large margin. Okay, so I hope you guys are by now convinced that it's really important to also understand more deeply what's going on in these learning systems, because they can help us design algorithms, they can help us reason about making sure that we do well and we just things that are not looking good just by luck. Okay, but this is one of my favorite examples that shows that a deep sample complexity statement can suggest an algorithm. Okay, and so this statement about large margin actually was known from the 70s, but somehow actually the SVM algorithm that I'm going to discuss about at the end of the lecture didn't quite take off at the time, and the reason that it didn't quite take off is because this statement was known in the context of linear decision boundaries. And very few things are linearly separable. Okay, and actually this perfectly motivates my next topic, which is kernels. Okay, so before talking about SVM, I want to first talk about kernels, because SVM didn't become popular before we had kernels. So any questions at this point? Because now I'm going to switch topics. All right, so if there are no questions, let me go on. Okay, so far basically we talked about margins in the context of linearly separable or nearly linearly separable distributions or data sets. We know, however, we all know that in most learning problems, the data is actually not linearly separable. So there are some data sets or there are some domains where data could be linearly separable, like text classification. However, for most learning problems, the data is not linearly separable. So for example, if you want to do image classification, the data is typically not linearly separable in the most natural pixel representation. It's actually not even linearly separable if you consider more fancy features like wavelets and so on. Okay? Now, there are a number of ways to try to address this problem, and we've already seen some in the course, like we can try to use decision trees or boosting, and older ways to use neural networks, and other more modern ways to use deep networks. But today we're going to talk about a very neat, interesting solution that attracted a lot of attention in the past decade or decades, namely to use a kernel function. Okay? So, I hope that you are guys by now all curious what is a kernel function. So, and actually I'm going to start with the punchline, okay, before going, and then I'm going to go slowly for what kernels are. So, at a very high level, what kernel functions are a special type of similarity functions, pairwise functions, that in combination with a special type of learning algorithm, will allow us to find non-linear decision boundaries. Okay, and to be a bit more concrete, still staying at the overview level. So what is a kernel function? Well, a kernel function is just a pairwise function that can be viewed as a legal definition of a dot product. Okay, so in other words, K, which is a pairwise function, is a kernel function if there exists an implicit mapping phi into a possibly very high dimensional feature space, such that K of xy is a dot product between phi of x and phi of y in that higher dimensional feature space. Okay, and here's just, if you are very curious right now, here's an example of a kernel function. This is called the so-called polynomial kernel, and you're going to see it in detail in the next part of the lecture. Okay, so kernel function is just it's a pairwise function that corresponds to a legal definition of a dot product. Okay, now why are kernels important? Well, it turns out that many learning algorithms, like the Perceptron algorithm that we discussed, and also the SVM algorithm and many other learning algorithms, can be written or can be rewritten so that they interact with the data only via dot products. Okay? And that means that if we then replace a dot product computation with a kernel computation, then our algorithm will act implicitly as if the data was lying in the high-dimensional feature space. Okay, but to do so without having to pay a high price computationally, without having to ever go explicitly into the higher dimensional feature space. Okay, so that's we get here computational savings. So it's a smart trick from a computational point of view. Okay, but now we go into higher dimensional feature space. You should be all worried. I mean, it could be infinite dimensional feature space. You should be all worried to overfit. Right, but here is the second point, and this is related to our discussion so far. Well, if the data is, say, linearly separable by a large margin in the higher dimensional feature space, then according to the discussion that we just went through, we are guaranteed that we're also going to get good generalization abilities as well. We're not going to overfit. Okay, so we're also going to get good sample complexity guarantees. Okay, that's the punchline of an overview of kernel methods. And I just want to make a quick comment. This is a more technical comment. So large margin. So really, what we need in the high-dimensional feature space is to have some sort of regularities to control somehow the capacity. Large margin is a nice way. It's a traditional way. But there are other ways to control the capacity in the high-dimensional feature space too. Okay. But this is the most intuitive one to think about. And for this course, this is sufficient. Okay, so this is the overview of kernel methods, and now I'm going to go slowly through what kernels are, and I'm going to go through examples. Yes?
So is phi a convertible map, or so phi is a map, right?
Yes.
So is it invertible, or is it an isometry? Like what kind of map?
We never want to think about, okay, let me go more slowly. I never want to think even about inverting phi, because I never want to go very explicitly. So, and phi might not even be unique. Okay. So let's go more slowly. Okay, so that's an excellent question. So you should re-ask the question as I go through. Okay, so let's just go more slowly. Actually, so what is a kernel? Okay, so phi actually, let me put the definition right now. So phi might not even be unique, right? So all I care about from the point of view, right? So from the point of view of the algorithm, from the point of view of using kernels inside the learning algorithm, all I really care about, and that's the important aspect, and this is what you should remember, and I'll make this explicit as I go through, what I really care about is when my kernel corresponds to a legal definition of a dot product. I will never want to write down phi of x in my algorithm, or phi of z. All I want to do is to write down k of xz. Okay? And let me go through this slowly. Okay, so what is a kernel function? Well, it's a pairwise function that can be viewed as a legal definition of a dot product. Okay, so in other words, k, a pairwise function, is a kernel function if there exists a mapping phi into, this is an implicit mapping phi into a potentially very, very high dimensional feature space, which actually can be even infinite dimensional feature space, with the property that k of x, z is a dot product between phi of x and phi of z. Oh, and by the way, I use here z instead of y because y for me it's always a label. Okay, so I picked a different, I'm using x and z instead of x of y and y because yeah. Okay, in any case, right, so k is a kernel if there exists a mapping phi, might not be unique, right? So k is a kernel if there exists a mapping phi into a potentially very high dimensional feature space such that the dot product between phi of x and phi of z in that higher dimensional feature space is k of xz. Okay, and I'm going to call the range of the phi space, I'm going to call it the phi space, and the key point is that n can be very, very large. It could be even infinite for certain kernels like Gaussian kernel. And that's a very crucial point that is related to your question. I want to think about phi as being implicit and not explicit. I never want to compute phi explicitly. All I want to do is to use in my algorithm k of xz. Okay, and let's look at an example. Okay, so here is a classic example. This is actually stolen from Alex Smola's book. So actually, Alex Smola, which is the professor here, he is one of the promoters of kernel methods in machine learning, and he wrote a book on the topic, and here's his classic example. So, right, so let's assume that the data lies in a two-dimensional feature space. So this is the ambient space, the original feature space, right? And let's assume that we have points that are not, obviously this is not linearly separable, but these points are linearly separable, they are not linearly separable by an ellipse. Yeah, so this is the original data set. So the points are separable by an ellipse in the original feature space. And I also claim that we're going to be linearly separable by, in the phi space corresponding to polynomial kernel of degree 2. Okay, and what is this quantity? So this thing over here, k of xz, so so this is D is the degree of the kernel, and this is a classic example of a kernel function. So K of xz is simply x dot z to the power of D. Okay, and just to make it even more concrete, in my example, n equals 2, and because it's simple to write it down, I'm going to think about D as being 2. Okay, and I'm going to claim that this is an example of a phi mapping corresponding to this kernel K. Okay, so what I'm going to do, this is x is my original example, right? Let me try to see if I can use, right? So this is my original example x, and I'm going to map it into phi of x. So I have two original coordinates, x1, x2, and I'm going to map it into phi of x, where I'm going to have three features now. I'm going to have a feature corresponding to x1 squared, the feature corresponding to x2 squared, and the feature corresponding to square root of 2 x1, x2. Okay? And obviously, if this is my phi mapping, I'm going to convince you in the next slide that this is a phi mapping. But if this is my phi mapping corresponding to this kernel, right? If this is actually, if phi of x dot phi of z is equal to this quantity over here, k of xz, then you should believe me that, yes, indeed, the data is not linearly separable in the original feature representation, but it is linearly separable in this new feature representation, three-dimensional representation corresponding to this polynomial kernel of degree 2, right? Because what is an ellipse in the original feature space? Well, an ellipse looks like, so this ellipse looks like x1 squared over a squared, oops, plus x2 squared over b squared equals a constant, right? This is what an ellipse is, right? So the data is separable by this decision surface. It looks like x1 squared over a squared plus x2 squared over b squared equals a constant. And because of this, then clearly this immediately implies that it is linearly separable in this higher dimensional feature space, right? Because I'm going to have non-zero coefficient on the x1 squared and on x2 squared, and the zero coefficient here, and that this decision surface immediately corresponds to a linear separator in this two higher dimensional feature space. Right? Is the example clear to everyone? Right? So if I convince you that basically this mapping phi that maps examples x1, x2 into this higher dimensional feature space phi of x, if this is a mapping phi corresponding to the polynomial kernel, then I immediately get that my data is not linearly separable in the original feature space, but is linearly separable in is separable by an ellipse, and is linearly separable in the phi space corresponding to this polynomial kernel of degree 2. Okay, and let's just quickly go slowly of why. Yes.
So that plane would be parallel to the one of the axes, right?
Yes.
You have shown it as tilted.
Okay, it should be parallel to one of the axes. Yes, absolutely, because I have a 0. Yes. Yeah. No, it's not tilted. I guess it's parallel to these three axes. Okay. Yeah. But you're perfectly right on the target. It should be parallel to the three axis. Yeah, to the third axis. Excellent. So that means you're following the example. Great. So I like when you guys ask questions because good. All right. So let's quickly see. That's very, very simple to actually see that this is really a legal phi mapping for this kernel. Right. So if you recall, the kernel was k of xz was x dot z squared. Right. So it's degree 2, polynomial kernel of degree 2, and it's very immediate to verify that phi of x dot phi of z. Right, so what if I look at phi of x dot phi of z, what is phi of x is x1 squared, x2 squared, square root of 2, x1, x2, right? And dot the phi of z, which looks like this, z1 squared, z2 squared, square root of 2, z1, z2, right? And then if I take the dot product, how do I take the dot product? I go coordinate by coordinate and multiply the coordinates, and then I sum them up, right? If I do so, what do I obtain here? I get x1 squared times z1 squared plus x2 squared times z2 squared plus 2 times x1, x2, z1, z2, okay? And now if you remember a basic fact about a plus b squared is a squared plus b squared plus 2 times a times b, then we immediately get that this can be rewritten as being x1 z1 plus x2 z2 all squared, which is identical to x dot z squared, right? So hopefully I convinced you that this function over here, x dot z squared, is a kernel. Why is the kernel? Because there exists a mapping phi from the original feature space into this three-dimensional feature space, so such that k of xz, which is x dot z squared, is identical to phi of x dot phi of z, the dot product between phi of x and phi of z in this higher dimensional feature space. Okay, so that's a legal kernel function. Yeah? And to go back to your question, actually, because you're asking is the invertible, actually the mapping phi might not even be unique. Right? So to show that a kernel function, a pairwise function is the kernel, I just need to show that the mapping phi exists. And in fact, typically they are not even unique, these mapping phis. right? So for example, for the same kernel, I can map into a 4-dimensional feature space. I can go from the original feature space, which is 2-dimensional, into a 4-dimensional feature space, that now looks like I can go from, so this is x, which is x1, x2. I can go to this 4-dimensional feature space that I have a coordinate for x1 squared, another for x2 squared, one for x1, x2, and another one for x2, x1. Okay? And you can quickly verify, I'm not going to go through the computation, you can verify basically that if I now put down phi of x dot phi of z, the dot product between these 4-dimensional vectors is identical to x dot z squared, which is my original kernel. Okay? It's just another data point, right? As I mentioned, to talk about a kernel, I need to talk about a pairwise function, kind of a similarity function, pairwise function, and x is my first argument and z is my second argument. Okay, that's a great question. And so for the lecture, for the first part of my discussion, I'm going to assume that somehow I'm given a good kernel function. That somehow, yeah, that's domain knowledge basically. Or you can also talk about learning the kernel function.
So can I create another kernel function projected to?
Okay, so let's come back to this discussion after we go through more basics about kernels. But that's an excellent question. How do you know how do I come up with the kernel? Okay, and right. Before even talking about how do I come up with a kernel, I need to first understand properties of the kernels, right? Because I need to know what I'm looking for, right? And that's why I want to go for more elementary discussion relating kernels and margins, and then we can come back to the discussion. Yes?
Can we know for sure, like, that it can be moved to a higher dimension and separated? Like, we are moving it to a different, greater dimension space, but are we sure that we can separate it once we do that?
Not necessarily, right? I mean,
did we do a check for it before we moved it?
So right now, I just want you to understand what kernels are and when are kernels good, right? So we should come back to this question. It's related to her question. Your name is? Sai. Okay, so right. So your question is related to her question. How do I choose a kernel? And I think it's good to talk about this after we talk about what is a good kernel first, right? Because before talking about how I'm looking for a good kernel, I need to understand what is a good kernel. Right, so far I only talked about the legal, what is a kernel. I just told you what is a legal kernel. So this is what a legal kernel is. A legal kernel is just something that corresponds to a legal definition of a dot product. So a pairwise function K is a kernel if there exists an implicit mapping phi into a possibly much higher dimensional feature space such that K of xc is phi of x dot phi of z. Okay? So I need to tell you what good kernels are. So this is a legal kernel, but I need to tell you what good kernels are. I need to show you that there are some algorithms that can use kernels. And then once I understand all these, then we can go back and think about how do I design the kernel, how do I choose the kernel, how do I learn the kernel. Okay, but first we need to understand why they're interesting. Okay, and it's very crucial, yeah? I'll take the next question, yeah?
Can phi be another kernel? Like kernel?
So phi is a one that takes, K is a pairwise function. Phi just maps one single point. Yeah, so they're kind of different quantities. Yeah? But actually, so that's a good question. Yeah? Definitely. Okay, so but actually one point that I really want to make and before going on is that it's crucial to think about phi as being implicit and not explicit. We never want to go back into the phi dimensional feature space. Okay? As to go into the higher dimensional feature space. You never want to do that. Okay, and this is a slide that I stole from my friend Lee Song. So for example, he showed that if we think about, right, so we went for the polynomial kernel of degree 2, but in general we can have a polynomial kernel of degree d, right? And then you can think about what is the dimension of the phi space corresponding to the polynomial kernel of degree d. Well, it turns out it is very, very large. So for example, if we have n equals 100 and d equals 6, then if we think about the phi space that we're going to have 1.6 billion terms, we never want to go into the higher dimensional feature space explicitly. Yeah, so that's a crucial aspect of kernels. The crucial point is that, for example, right, for this polynomial kernel of degree d, the higher dimensional feature space could be huge. However, so we never want to go explicitly there. However, for example, as shown here, we can actually compute the kernel function by only using linear time in the original feature space. Right, so we can compute K of xz by only using x dot z to the power of d. I can say in the original feature space, the running time depends only on the dimension of the original feature space, and I still can compute K of xz. Okay, so we never want to go explicitly into the high dimensional feature space. Okay, but now, how do I use kernels? Okay, so, okay, I said I don't want to go explicitly into the high dimensional feature space. Why are they useful? Okay, and here is why they are useful. And this will relate to Perceptron and SVM and everything else. Okay, it turns out that so there are some certain types of learning algorithms like Perceptron or SVM that can be kernelized. And what do I mean by kernelization? It turns out that if all the computations involving instances are in terms of dot products, then I can replace the dot product computation with a kernel computation from a computational point of view. Okay, and then conceptually, my algorithm will work as if the data was mapped into the higher dimensional feature space, but I never had to do that mapping explicitly, right? So if I replace the dot product computation with a kernel computation, I will get the exact same behavior as if I map the data into the higher dimensional feature space, and then the learnability guarantee is not only going to depend on the performance or depend on the properties of the data into the higher dimensional feature space. Okay, but computationally, I get savings because I never do that mapping explicitly. Okay, I compute the kernel K of X staying in the original feature space. Okay, so that's when kernels are useful. Kernels are useful if into the higher dimensional feature space data has some nice properties, like it has a large margin, and moreover, if I can use kernels with a kernelizable learning algorithm that have the property that all the computations involving instances are only via the products. And it turns out that many learning algorithms in machine learning are kernelizable. I have a list here, but let me just to be concrete and just go and run through kernelizing the Perceptron algorithm. Okay, because we've just done it. Okay, so let's go slowly and see why the Perceptron algorithm can be kernelized. Okay, so we've seen the algorithm already at the beginning of the lecture, and we already know, right? So it's a very simple greedy procedure, and we already know, I went through this in detail, that so this is an algorithm for learning linear separator. At each moment in time, I have a current guess for the target, WT, after t mistakes. And we already seen that basically at any given moment in time t, my weight vector is a weighted combination of examples on which I made a mistake. Okay, and because of that, that means that in order to be able to predict what happens on a new example x, all I need to be able to compute is a dot product between my current guess for the target and the new example x. But if I expand this out, that means that all I need to be able to compute is dot products between the mistakes I've made and the new example x. And to be able to compute the dot product between points xi1, xi2, and so on, xik, those are points in which I made mistakes, and my new example x. Okay? Well, this is, as you can see, this is a learning algorithm where all I need to be able to do is to compute dot products between instances. Right? So that means I can kernelize it because I can replace this dot product computation xi1.x with a kernel computation k of xi1x. Right? And so on. I can replace xik.x with a kernel computation k of xikx. Okay, and if I do so, then my algorithm will operate as if I map the data into the high dimensional feature space and run the Perceptron algorithm there. Okay, there is one difference from the classic Perceptron or run the Perceptron unkernelized Perceptron. In order to be able to run the kernelized Perceptron, I actually need to store the mistakes. I need to store these examples on which I made the mistakes. I need to store the mistakes xi1 and so on, xi2, xik. Because given a new example x, I need to be able to compute this quantity over here, this weighted linear combination of kernel computations. So I need to store the examples on which I made mistakes. Okay, and just to be even more explicit here is basically the kernelized Perceptron, right? So assume that I made t-1 mistakes so far, and let's assume that my mistakes are xi1, xi2, xit-1. So I made mistakes on examples xi1, xi2, xit-1. Given a new example x, I'm going to predict positive. This weighted combination of kernel computations is positive and negative otherwise, right? And if I do make a mistake, because I'm told the label at the end of the day, right? If I do make a mistake, if it's a mistake on a positive example, I'm going to store the example xit that I made a mistake on. And I'm also going to store the coefficient AIT to be 1. I'm going to remember the coefficient AIT was 1, right? Because remember, if I make a mistake on a positive example, I need to add the example. Okay. Similarly, if I make a mistake on a negative example, I'm going to store this xit, and I'm going to set the coefficient to be -1. Okay. And then I claim that if I do so, and I totally simulate the behavior, so if this algorithm will be identical, right? Because here, okay, why? Because k of xit-1x, for example, is the same as phi of xit-1 dot phi of x by the definition of the kernel function. Because of this, right? And this is true for all these terms over here. Because of this, I claim that I get the exact same behavior as if I first map the data into the a phi space corresponding to my kernel, and then running the perceptron algorithm there. So the algorithm that I just have on the slide is identical to that algorithm. But the cool fact is that I never have to map explicitly the data into the higher dimensional space, into the phi space. I just stay in the original feature space, and this is much more computationally efficient, for example, for the polynomial kernel and for most kernels. Okay, so I get the exact same behaviors running perceptron into the higher dimensional feature space, but I get computational savings. So this is the whole trick. It's a super smart trick, very interesting trick. Okay, and we get computational savings by doing so, and moreover, like we know that we care not only about doing all over the data, right? We also care about, or like in the online learning model, we want to minimize the number of mistakes. And so we also have to think about what happens to the data into the higher dimensional feature space. And I already mentioned, well, if in this higher dimensional implicit phi space, if the data has some nice regularity properties, for example, if it has a large margin, then I'm guaranteed that perceptron are going to make a number of mistakes that only depends on the margin of that high dimensional feature space and not the dimension of that phi space, which could be huge, infinite, right? It would be terrible to have a dependence that depends on the number of mistakes that depends on the dimension of the feature space. It would not be good. But it turns out that if the data has a large margin in the phi space, then the number of mistakes depends only on the margin. Yes?
When we shift from a lower dimension to a higher dimension, the R also increases?
Could, right? So when the number of absolute I mean, it could. Yes, so when the guarantee, that's an excellent point. That's why I have R here. R there is basically R in the mistake bound will depend on the length, for example, into the phi dimensional feature space. The maximum length, on an example coming from my distribution, from my data set, into the high dimensional feature space. It does. It typically does. Yeah, you're totally right.
So the generalization guarantee goes down, like it will take more examples than how.
If R is large, it depends on your data set, depends on your kernel. Right? So all we can say mathematically is that if, right, so the number, formally the number of mistakes that my kernelized perceptron algorithm is going to make, so for example, in this online learning model that we've been discussing perceptron, the number of mistakes that my kernelized perceptron algorithm will do is actually R squared over gamma squared, where gamma is the margin of the data set S mapped into the phi dimensional feature space, and R is the maximum length of an example phi of X. So this should be, R here is the maximum, just to be, let me write this down actually. So R is maximum over X in my data set of the norm of phi of X. What's going on with my pen? I need to more aggressive. Oh. Something strange going on. X in S. Oh no. Okay, something wrong is with PowerPoint. Okay, you get. Okay, good. So, but all I wanted to say here is R here, right? Okay, great. So this is R. So R is this quantity over here, the maximum norm, the maximum length of an example phi of X, where X belongs to my set of points as I've seen. Yeah? So basically, the mistake bound is going to depend on properties of the data when mapped into the high dimensional feature space. But the key point, and if the data has a large margin, for example, the number of mistakes only depends on that. But the key point is that I never have to go very explicitly. I can do that. I can kernelize the perceptron, and I can get smart computational savings. Okay, cool. And let me just give a couple more examples of kernels. So far you've seen the polynomial kernel, the so-called polynomial kernel of degree D. Let me give you a couple more examples of kernels, widely used kernels. So, right, so this is the polynomial kernel that we discussed. So the feature space here corresponds to all monomials of degree D. There is a related kernel where the feature space corresponds to all monomials of degree up to D. Okay, so you can verify these things. If you are curious, I have a lecture note. You can go in detail for them offline. Okay, I just want to also mention actually the most trivial kernel we can think of is the linear kernel, right? K of xz is x dot z. I claim it's a kernel. Do you guys see why? Can somebody give me a quick proof? What would be a legal mapping phi? Itself, phi of x is x, right? So I just wanted to mention this because this is a simple test that we are on the same page, right? So so the most trivial kernel, the dot product K of z is a legal kernel, good. But more interesting kernels are the polynomial kernels, and widely used kernels are the polynomial kernels. Two forms of these kernels. So the first one is K of x is x dot z to the power of d for some d, and the second one is 1 plus x dot z to the power of d, okay? And another kernel, right, and the feature space is very large here for the polynomial kernel, but it's finite. it's roughly, and in both cases, of the order n to the power of d. Okay? But there is another widely used kernel in practice, which is called the Gaussian kernel, and the feature space varies infinite. Okay, and this is looks at the form. If the kernel is of the form k of xe is e to the minus norm of x minus e squared over 2 sigma squared. Okay, and actually, in order to talk about this mathematically, and I'm not going to do this in this course, how to even talk about infinite feature spaces, you need to use functional analysis and talk about reproducing kernel Hilbert spaces. And so you need to put a lot of formalisms in order to be able to talk about a dot product into an infinite dimensional feature space. Okay, but there are books that do that. It's beyond the scope of this course. I just wanted to mention that. To be totally formal, you need to use a little bit more technical details. But what's important anyway, from the point of view running the algorithm, it's all you need to know that this is a kernel. It's not important to know all that formalization. Okay, and there are also, so this is the Gaussian kernel. I think it's one of the most widely used kernels. It has a sigma parameter over here that one can tune. There is a related kernel called the Laplace kernel, where instead of having squared here, e to the minus squared distance, we only have e to the minus z distance between x and z over 2 sigma squared. And as you can see, both these kernels are very easy to compute. Okay, and there are also many other kernels. So these are kernels, what I wrote down, these are kernels for vectorial data. There are also sorts of kernels for non-vectorial data, like strings and so on. And yeah, there are books and many, many papers have been written on the topic. So yeah, it has been a widely popular topic. Okay, so these are just examples. I also want to mention, because this is a classic fact about kernels, I just want to mention it. Because you might now wonder, how do I prove that a function is a kernel, right? How do I construct a new kernel? So, and why do people write kernels, right? First of all, how do I even prove that a function is a kernel? A pairwise function is a kernel, a legal kernel. Okay, so here is a classic result that everyone likes to mention. So it turns out that a pairwise function k is a legal kernel if it satisfies two properties. So first of all, k is symmetric. So k of xz is the same as k of zx. And it's positive semi-definite. Okay, what does it mean? It means that basically, if I have any set of training points, x1, x2, xm, right, and if I think about the kernel matrix k that this set of points induce, right, so if I have, these are my set of points from the original instance space, and if I think about the kernel matrix where I put, for entry ij, I put k of xi, xj, this is called the kernel matrix, right? This kernel matrix is positive semi-definite. Okay, meaning that if I take any vector A, now if I take any m-dimensional vector A, and I think about the A transpose Ka, this is greater than or equal to 0. Okay, so this is a necessary and sufficient condition for a pairwise function K to be a kernel. It's called the Mercer theorem. Okay, so K is a kernel if it's symmetric, and moreover, for any set of points from the original instance space, the corresponding kernel matrix, which is basically a matrix that has m squared entries, ntij corresponds to the kernel computation between xi and xj. Well, this matrix is positive semi-definite, meaning that basically for any vector A in Rm, I have that A transpose K is greater than or equal to 0. Okay, so this is one way in which you can verify that a function K, a pairwise function K, is a kernel. Okay, so you can, for example, you can use this to verify that the Gaussian kernel is a kernel, or that these other examples that I had on my slides are kernels, legal kernel functions. Okay, so now you might ask, okay, so that's a necessary sufficient condition for a function, a pairwise function K, to be a kernel. Now you might ask why, so I mentioned actually, but let me say it again. I think in the last decade in machine learning, kernels were probably the most popular method for handling nonlinearity. Okay, they still remain popular today. There are other competitors these days, but definitely in the last decade, they are the most popular method. Okay, and you might wonder why are they so popular? Okay, what is so great about them? And here is the argument that people made. Okay, so well, it turns out that kernel methods are interesting because they offer some sort of modularity in multiple ways. So the first way is that basically, once we have a kernel function, right, we don't need to change the underlying learning algorithm in order to accommodate a particular choice of kernel function. So we can still use Perceptron and try various types of kernels. Okay, so that's one sense in which the kernels are modular. And another sense in which they are modular, we can also keep the same kernel, but with a different learning algorithm. I could substitute Perceptron to SVM, to logistic regression, to ridge regression. So I could take another kernelizable learning algorithm and keep the kernel fixed. Okay, so they are kind of modular methods. Okay, and this is one of the arguments for which they became so widely used and so popular. Okay, and they're simple to think about, yeah, and many algorithms are also kernelizable. Okay, now another nice fact is, okay, so these kernel functions have some nice closure properties. So in particular, we can easily create new kernels by using basic kernels. Okay, and here is one composition property. Here, if I have two kernel functions, K1 and K2, right? These are two pairwise functions that are legal kernels. They correspond to legal definitions of the product. When I claim that the linear combination, weighted linear combination with positive coefficient, any weighted linear combination with positive coefficients of these two kernels is a kernel function, is a legal kernel function, will correspond to a legal definition of a dot product. Okay, and to make sure that you guys follow me, I'm going to ask you for an idea for arguing this. It's actually not hard. So how do you prove this fact? So that's a fact. It's a simple, neat fact about kernels. I have some nice closure properties, and here is one simple closure property. If I have two fixed kernels, if I think about any weighted linear combination of those two fixed kernels with positive coefficients, I claim that's a kernel. And this fact has a simple proof, right? And I think it's not even a proof, an argument, okay? So I'm trying to involve you into coming up with the argument.
Actually, the first property is that it should be symmetric, which can be easily proved by taking in different kernels and then substituting.
Sure.
And the second property.
I see. So you are trying. Okay. So how do you prove that the pairwise function is a kernel? So you are. HEMA, right? So HEMA is trying to use the Mercer theorem that I mentioned in order to prove this is a kernel, right? Trying to show that it's positive semi-definite. Yeah. Right? There are multiple ways to try to prove that a function is a kernel. One way is to use the definition, one way is to use the Mercer theorem, one way is to use actually these closure properties that I'm going to discuss. Okay? Now the simplest case here is actually the simple one of the, okay, they're all simple actually. But one simple way is to use the basic definition. So if I know that K1 is a kernel, so it has a phi space, a phi1 mapping space, and if K2 is a kernel, has a phi2 mapping space, then it's kind of easy to show a phi space for this K function, for the weighted linear combination. But definitely you are right. You can also go through the Mercer theorem, and actually I'm sure you can do it. It just requires writing more equations down. Okay, so the simplest one that I could use on my slide would be to just use the basic definition. So do you guys see? Anybody sees? Yeah, you see it? So how would I show it?
You can expand out like the kernels by using the phi space like you're talking about, and then you just define a new phi function based on the linear combination of those.
Okay, perfect. So in other words, I can just concatenate the phi spaces. That's one simple way to say it. Okay? Right, so basically if I have a phi1 mapping for the first kernel, a phi2 mapping for the second kernel, I can just concatenate those two phi spaces. And then I immediately get that this is a legal phi space for the weighted linear combination. I can just verify, right, that if I put phi of x to be square root of C1, phi1 of x, these are, say, the first n1 coordinates if the dimension of phi1 is n1, right? And these are the n2 coordinates here if the dimension of phi2 is n2. Right, I can define phi of x this way, and I can quickly verify that if I have 2 points, 2 instances, phi of x and z, I can verify that phi of x dot phi of z, when I did the dot product between phi of x and phi of z is exactly C1 phi of 1 of x dot phi 1 of z plus C2 phi 2 of x dot phi 2 of z, and that's exactly K1 of xz, and this is exactly K2 of xz. Okay, so it's very simple to show that the weighted linear combination of two kernels is a kernel by using the definition. Okay, cool. And right, okay, how about, so this is one nice closure property. So weighted linear combinations of kernels are kernels. It turns out that the product of two kernels is a kernel too. And the proof here is a little bit more involved. So I mean, a simple argument, it's okay. So it's simple, but okay, it's a little bit more involved. So it turns out that now if I can just again use the basic definition. There are many ways to prove this fact, but one way to do it is to use a basic definition. And the existence of a phi mapping. So if I have a phi mapping for the kernel K1 that goes from the original feature space into an n-dimensional feature space, and if I have a mapping for the kernel K2 that goes from the original space into an m-dimensional feature space, then I can construct a feature space for the product of the two kernels, or I go into an n times m-dimensional feature space by somehow doing the what's called, I think, the tensor product between these two, between phi of x, between the two dimensional feature spaces. Okay, so formally I'm going to have I'm going to now go into an n times m dimensional feature space, and the ij entry are going to correspond to phi 1 I of x times phi 2 j of x, where I goes from 1 to n and j goes from 1 to m. Okay, and then I'm not going to go for the computation, but you can verify it actually that if you go for the computation, I'm not going to go into detail for the computation, but you can verify that if I then go ahead and expand compute phi of x dot phi of z, I write down what that is. It's sum over all ij of phi 1 I of x, phi 2 j of x, phi 1 I of phi 1 I of z, phi 2 j of z, right? And then I notice that some of these terms depend only on I, and some depend only on j. And if I rewrite this sum in this way, I can just pull out all the terms that involve only j here, and then I notice that this is exactly identical to k2 of xz, and I can factor this out, and then I just go through the math. I get that phi of x dot phi of z is exactly k1 of xz times k2 of xz. Okay, so I claim that the product of two kernels is a kernel, and you can just verify it by showing a corresponding phi space, which is just a tensor product between the two phi spaces corresponding to the two kernels. Okay, so I know that this was quick, but believe me. Okay, but well, this immediately implies, for example, that so these are two basic facts that can help us prove that many functions are kernels, right? So I mentioned that x dot z is a kernel, right? I mean, the basic trivial linear kernel. Well, I can use that immediately to show that x dot z to the power of d is a kernel by just using these two facts, because weighted linear combinations and products of kernels are kernels, and if I think about what x dot z to the power of d means, then I immediately get that it's a legal kernel by using these two facts, and the fact that x dot z itself is a kernel. I can then use these facts to then prove that the function that I had earlier on my slide, like the Gaussian kernel is a kernel, right? So I can then go back and prove. So by using these closure properties, I can immediately prove that some of these, like this is a kernel, the Gaussian kernel is a kernel, and so on. Okay? So it turns out that kernels have nice modularity properties, they have nice closure properties, and we can easily construct new kernels starting from basic kernels. Okay, and moreover, right, as I mentioned, okay, to just basically go back and say again why they are useful. It turns out that they are useful with certain types of learning algorithms like perceptron or SVM or linear regression. So those are learning algorithms that can be written so that they only interact with the data via dot products only. Okay, and so that means, as we showed in the perceptron case, that means that we then replace a dot product computation with a kernel computation. Our algorithm is going to act as if the data was mapped into the higher dimensional feature space, but we never have to do that mapping explicitly. So you get computational savings. Okay, and moreover, the mistake bound, if you're an online learning scenario, or the generalization ability, the sample complexity, if you're in distributional learning setting, only going to depend on the properties of the data in that higher dimensional feature space. So for example, if you have a large margin, we'll also get good generalization guarantees. Okay, and right, so it's actually very important to remember, actually. So one thing is when kernels became very popular, people are just proving that certain pairwise functions are legal kernels. But it's actually important to remember that we care not only about legal kernels, but we also care about kernels that have some nice regularity properties into the phi space, to the high dimensional feature space. Like they must have a large margin or some other type of regularity property like spectral decay and so on. Because we can always map any data set into high dimensional feature space by a kernel, so that would be another homework question. But sometimes this mapping might not have a large margin, for example, right? We cannot easily overfit. So it's crucial to remember that for a function k to be good, it has to be a legal kernel, but also has to have some nice properties like large margin to the phi space. Okay? And now with this in mind, for example, going back to your question, I might ask, how do I know the kernel, okay? Like how do I choose the kernel, right, if I have a real world problem, right? And one classic solution is what people always try to use Gaussian kernel. For example, this works often. It has a sigma parameter that can be tuned by, say, cross validation. So that's one solution. But people have also talked about learning the kernel. Like if I have a base family of kernels, I can think about like K1, K2, KL. I can think about what's the best convex combination of these kernels with respect to my data, and how do we define best? Well, the one that has the largest margin, because I know that a good kernel is one that has a large margin. Right? So I can use the understanding of what a good kernel is, one that has a large margin, to then design a learning algorithm. Okay, and actually there's a celebrated work in like 2000 by Lancreate, Jordan, and others that were doing exactly this. So we're trying to learn a kernel from as a convex combination of a base family of kernels, and the explicit optimization procedure that they had is we're trying to learn a kernel that had a large margin.
What is the reason behind if you project data to infinity and that is separable?
It might not be. So that's what I'm saying. So for the data, okay, so it might not be to infinity. Okay, it is separable. Okay, no. So I think you can always show, okay, the Gaussian kernel is what people call it a universal kernel. So I can always, in the phi space corresponding to the Gaussian kernel, the data will always become linearly separable. But it might become linearly separable, but not by a large margin. So it's crucial, again, in order for the kernel to be good, not only to be linearly separable into the phi space, in the infinite high dimensional feature space, but has to have some sort of margin, because otherwise I'm going to overfit. So that's crucial. So is this point clear to everyone? So for a kernel to be good, I must have some nice properties into the phi dimensional feature space, must have a large margin. Right, there are kernels that are Gaussian kernel that are called universal kernel. If I go into the phi space corresponding to the Gaussian kernel, anything becomes linearly separable, but it might not be linearly separable by a large margin, right? And if I have to rely on basic sample complexity guarantees that depend on the dimension of the feature space, and then it would be horrible, right? Obviously, I can overfit. And actually, I only have a few more minutes left. I just want to mention maybe, rather than going for SVM, actually, when I was a student, actually, one of my first papers was showing, actually, turns out that you can formally show that if you have a large margin to the higher dimensional feature space, you can project the data into a much lower dimensional feature space. You can do a random projection and project the data into a much lower dimensional feature space and still preserve the separability and the margin. Right? I'll bring this picture next time. So I had a cool picture where the data was not originally separable in the original space. It was linearly separable into a much, much higher dimensional feature space. But it turns out that you can use some cool geometry arguments to argue that if you then project the higher dimensional feature space using a random projection, then the data will become linearly separable into a much lower dimensional feature space. And so then you could ask questions of the type, can I use this fact that such a mapping exists, then go directly down. Actually, let me see. Maybe I have this picture if I go online to my website. Maybe I can recover this picture. Because I think actually that would be a more interesting thing to show then. Okay, I'll show you a cool picture about kernels that will help you understand kernels a little bit more. Not spelling my name right. Let's try this, okay? Yeah, so here's a picture to keep in mind. Right, so if I use, for example, the Gaussian kernel, right? So there are kernels called universal kernel, like the Gaussian kernel, that have the property that if I map the data, if I think about the data, how the data looks into the phi space corresponding to the Gaussian kernel, that's always linearly separable. Right? But again, the point is if it could be linearly separable, but if it doesn't necessarily imply that it has good generalization abilities, right? Because it could overfit because the dimension of the phi space is infinite, and really the number of samples we need will depend on properties of the data into the higher dimensional feature space, right? Okay, so it's crucial in order to get good generalization guarantees for kernels. It's crucial to remember not only that we need to consider legal kernels that corresponds to legal definitions of dot products, but we also have to have some sort of other properties like margin properties. Okay, and here's an interesting picture. So this was actually joint work with Avrim, Blum, and Santosh and Pala. So we showed here's a picture. The data, okay, so the data might not be linearly separable in the original feature space, like this is, but say that magically is linearly separable into the phi space corresponding to some kernel, right? But now, right, but turns out that if we then do a random projection of this higher dimensional feature space into a much lower dimensional feature space, where the dimension of this lower dimensional feature space depends just on the margin of the data into this higher dimensional feature space, then I still can guarantee that the data is linearly separable by a large margin. Okay? And so then this motivated the question, can I go directly down into this lower dimensional feature space Like, can I come up somehow with some randomized mappings that takes in points from the original feature space and produces a mapping into this low-dimensional feature space? And it turns out that the answer is yes, and actually this led to some sort of fast algorithms for using kernel functions.
So,
Yeah?
so you're saying you're doing the classification with the same dimension, but essentially you're not moving it to a higher dimension.
Say it again?
So essentially you're not moving it to a higher dimension, you just took it up and then you brought it back.
This is okay. This picture is just for us to help us understand what good kernels are. So the point is, again, good kernels are not only functions that correspond to legal definitions of dot products, but they also have to have some sort of margin to the high dimensional feature space. Right? And then there was, like, at the beginning of 2000, people are saying, well, I can use a kernel and somehow magically get the power of an infinite dimensional feature space without having to pay whatever a high price computationally. But an important point is to remember that for the kernel to be good, it must be that in the high dimensional feature space, the data is separable by a large margin. Okay, and then what we're pointing out is with this picture is that the data is not so high dimensional after all, if you can separate the data by a large margin to the high dimensional feature space. Why? Because it turns out that you can formally show, you can randomly project the high dimensional feature space in a linear way to a much lower dimensional feature space and still preserve linear separability and the margin. Okay, so but of course you never want to go up and then down. Right, you never, because I mean that defeats the whole purpose. And so what we're asking is, can you come up with randomized mappings that go from the original space into this much lower dimensional feature space? And it turns out that the answer is yes. And again, this led to, we proved it in our original paper, but then people followed up a lot on it and led to some fast algorithms for running kernel methods, like random kitchen sinks and so on. Okay, I'll discuss more about this next time. Yeah.
How is this different from the concept of dimensionality reduction? Like, say, instead of random projection, like projecting on the principal axis?
Yeah, so that's a great question. So dimensionality reduction, typically people think about it in an unsupervised manner. So when the data is not supervised, so it's just unsupervised with data and you want to project to preserve the L squared error, right? Here we care about preserving classification. So here we assume that in the phi space, but that's an excellent question, right? So here we care about in the phi space there is a good separator with a good large margin. And what we care about when we're doing the projection is preserving the properties of this phi space with respect to my supervised learning problem. If you do like SVD or PCA, you might not preserve linear separability, right? So that it's kind of a different objective.
In PCA, we take only the correlation between different attributes, different features, right? Whereas over here, they're also taking.
Yeah, so wide random projection turns out that this is sufficient. Okay, it's for a technical reason. Wide random projection is sufficient. That actually, I'm not sure if PCA would work here. It might not work actually here. They're just like the right answer here is PCA is just an unsupervised learning technique. You are trying to project the data. You don't even have labels in mind. You are trying to project the data and you are trying to minimize the sum of squared errors, right? While here we care about preserving the classification properties into the higher dimensional feature space. Yeah?
So the RT space have a higher dimension than the X, the original?
It could be smaller. It could be smaller. So like you could go from there. This is the original feature space. This is very, very high dimensional. And this one could be smaller. Right? And that's why actually could this lead to fast methods for solving kernel SVM. Actually, I had a more pretty picture, but somehow it's not here. Maybe it's. OK, this is the right picture. Yeah, so I mean, the right picture should have been you never want to go up into the high dimensional feature space because it's like dangerous. You just want to go directly down. OK, cool. So this finishes the discussion about kernels. And next time I'll talk about SVM, which is one of the most important algorithms in modern machine learning. And it was directly motivated both by margins and by kernels.